you, and then off we go. Okay, so it's time for the final talk of the day on proof logging for maximum satisfiability solving, in particular MaxCDCL with MDD encodings. So detail, please.
Yes, so I will tell you everything about proof logging Vandesande solvers. So I will not try to convince you again about the usefulness of proof logging, but I will straight go to what MaxSAT is. And after that, we will take a look at how to actually proof log MaxCDCL with some additional techniques to improve its performance. And finally, we will also show how to proof log BDD encodings of a pseudoboolean encoding. So what is MaxSAT? MaxSAT is actually the optimization variant of SAT, where you have a propositional formula and an integer linear objective over Boolean variables. So a solution is an assignment that satisfies the formula and that minimizes the objective value. So if you think then about proof logging from MaxSAT, you would think, well, maybe there is some native proof system available. There are some proof systems available that were purely developed for a theoretic study of proof complexity, and there are some that are solvers that are specifically designed for creating proofs in the proof systems they have designed. But none of these are state-of-the-art MaxSAT solver that is using a native proof system. So we can think about why would that be? And to have an idea about that, well, it's a good idea to take a look at what kind of MaxSAT solvers there are. So we have the SAT-based MaxSAT solvers, model improving, core-guided, and implicit fitting SAT solvers. They use a SAT oracle to guide their search, to search for optimal solutions, and how they search for the optimality of these solutions depends on the different category of solvers. And you have the bind and bound solvers, and that's a bit the odd one out in the sense that they do not make use of SAT solvers, but they solve MaxSAT natively. But what's important here is to see that they all use different reasoning techniques, and that is probably the most important reason why it's so difficult to come up with a native proof system for MaxSAT. So,
sorry, I can't just help connecting to Kieran. My apologies. So, but just to share, like when you're doing this constraint proof logging, where they say, but you can't do regular or something, and now you've done these things. I remember talking to a very senior colleague, MaxSAT expert, one of the leading members of that community, and discussing proof logging. And just doing it before that, he said exactly this was like 4 years ago, maybe, that, yeah, but no, you're not going to do proof logging for MaxSAT because there's such a diversity of techniques that, SAT has it easy. They all do CDCL. That's why we have proof logging. That's never going to fly for MaxSAT.
Yeah. So, well, how can you do proof logging then for MaxSAT? First idea would be, well, proof logging and SAT is such a beautiful success. Why don't you try to use one of these proof systems for SAT? But these proof systems cannot reason about optimality. So how can they actually prove the optimality of a solution? A second idea, why don't you leave out proof logging in the first phase, just run a state-of-the-art MaxSAT solver. Try to find an optimal solution with that. Then check if this solution is satisfying. Create a formula that says, I will find a strictly better solution. And run a SAT solver with standard proof logging, which we have already for so long to obtain a certificate of unsatisfiability of this formula. Well,
maybe
checking if
also connect there. Well, when we submitted the paper on MaxSAT proof logging, this was suggested by one of the reviewers afterwards. Yeah, okay, why are you doing all this work? Yeah.
Don't sweat. I mean,
yeah,
didn't you realize?
Can you not just do this instead? Run SAT solver, you have proof logging, and you're done.
So checking if the solution is satisfying, well, that's not too difficult, I guess. But creating this formula, well, a SAT solver cannot reason about this kind of constraints. So we have to encode it in a CNF, and that needs proof logging. But since a proof system for SAT cannot reason about these kind of constraints as well, that needs proof logging in a different proof system already. And let's say that would work. Let's say we would find a way to proof log this, or we would trust the implementation, the CNF encoding, still running the SAT solver with standard proof logging. So this extra call to a SAT solver will cause extra search to be done, which might have been already been done by the MaxSAT solver in the first step. So that's a bit annoying that this gives extra time necessary to create a proof. And even more importantly, this only proves that the answer is correct, not that the solver actually found it by reasoning correctly. So another idea, why don't we use a fantastic general proof system? That's why we're here, I guess. So let's try to use VeriPB. What has been done already with VeriPB and MaxSAT proof logging? First, there was QMaxSAT. And QMaxSAT is a very easy model improving solver that searches for better solutions all over again and introduces a CNF formula that actually encodes this model improving constraint. So the focus there was on these pseudo-Boolean to CNF encodings. Then there was core guided search in RC2 and CGSS with all of the techniques on board in these solvers. So that was actually the first state-of-the-art MaxSAT solver with proof logging. And coming soon, Bacosa, that's a solution improving solver, but it uses the dynamic polynomial watchdog encoding, and it has some really interesting but intricate, without loss of generality reasoning, that we had to deal with. But then this talk is about Benjamin bound. So a third solving paradigm and a little bit of solution improving search, because MaxCDCL kind of combines the two, but the core of the MaxCDCL solver is Benjamin bound. So we will start with that. What is Benjamin bound? Benjamin bound creates a search tree like DPLL and continuously updates the upper bound whenever a solution is found. So whenever a satisfying assignment is found, it keeps track of the upper bound of the current best time solution. Every time it runs into a node where it's obvious that this partial assignment cannot be extended to a solution that is strictly better, it backtracks. So what does MaxCDCL do? It creates a search tree, and in every node, it actually tries to find a better underestimate of the lower bound of the current partial assignment. And it does that by using some look ahead with unit multiplication, which I will explain in a few seconds. And also interestingly, whenever it needs to backtrack because it finds no better solution will be found in this part of the search tree, it learns a clause just as CDCL solvers do. So actually, MaxCDCL is a generalization of CDCL solvers in the sense that hard conflicts can still occur. That's just a clause that's falsified just as in SAT solvers. But now we also have what is called soft conflicts. And that means that what I think the lower bound for this partial assignment is for the objective value is greater than or equal to the upper bound. And in both cases, a new clause is learned. And actually, in reality, this is even implemented in glucose. So that means it's really just glucose extended with the soft conflicts. That's what the solver looks like. So how does this look ahead works? Well, we are in a node, we have a partial assignment, and we want to see what the lower bound of the solution of the objective value is in this node. So we try to assign all of the not yet assigned objective literals to false, so to non-custom occurring. If a hard clause is falsified or not yet assigned objective literal is assigned 1, then we know that the assumed objective literals, at least one of them, needs to be assigned 1. And we call that a local core. And it's called a local core because it depends on the current partial assignment of the current node in the source. We start here with the unweighted case. Later I'll show you how this is done with a weighted case. But after that, so once we have found the core, we start over with all of the objective littles that were not yet found in one of the previously found cores. So every core increases the lower bound by 1. Because in every core, at least one of them needs to be true. And whenever we have found enough of these cores, we can see that the number of cores is actually the lower bound, so a soft conflict is found. Yeah.
Sorry, the disjoint bit, do you literally just throw everything away and run the solver again?
No. It's only in the look ahead. So you're in a node. You're assigning some objective littles false.
Right. Okay. Yeah.
You stop and then you try. So let's look at an example.
Dieter, like 2 quick technical remarks. I don't know if you want to get rid of this. You are sharing your entire screen thingy, and I wonder if you lost the connect sound. I don't know if it would be easy to fix it, but the sound quality just went down. But we are still hearing you, so.
And I try to fix the sound.
Maybe spend 10 seconds, and then if you want this small blob thingy, I don't know why it's. If you can.
Not really annoying.
Can you just? What happens if you?
But
Maybe if you put it in dial mode, you get 3 times.
still.
No, you're still okay. Then please continue. Sorry, something was weird. Okay, never mind. Sorry. But you're not in full. Now you're in full screen. Fantastic. Please. Sorry. Continue.
So let's take a look at an example. We have a temporary objective that's initialized by the actual objective that we're looking at. And this is the current partial assignment in the current node. Okay. We have an upper bound of 3, so we want to find at least 3 cores in this case. So let's assume y1 to be false. This propagates x9 and x10. And now let's propagate y2 to be false. This propagates x11, and we still don't have found a conflict, so we can still continue. We assume y3 to be false, we assume y4 to be false, and this propagates to a conflict. So that means at this moment that y1, y2, y3, and y4 cannot be false at the same time. In MaxCDCL, conflict analysis happens in the same way as it happens in CDCL solvers. So it finds out that this conflict was caused by x2, x4, not y1, and not y4. So since this leads to a conflict, we know at this moment that given x2 is x2 false and x4 false, it follows that at least y1 and y4 needs to be true. So that's the first core. Let's try to find the second one. Oh, and also importantly, so in the next round of this look-ahead procedure, I will not use anymore y1 and y4 because they are already found in one core. Let's start again. So we assume y2 to be false. We assume y3 to be false, and this propagates y5. So that means that at least y2, y3, or y5 needs to be true, given this partial assignment. Yeah? Because otherwise y5 wouldn't have been propagated. So let's assume now that the same way another core was found, namely this one. So given the current partial assignment, y6 or y7 needs to be 2. So that means, given the current partial assignment, y1 or y4 needs to be 2, y2, y3 or y5 needs to be 2, and y6 or y7 needs to be 2. So given the current partial assignment, the lower bound is 3, which is greater than or equal to the upper bound. So we can say that we found a soft conflict. And just as in CDCL, we learn a clause based on the current partial assignment to prevent the same current partial assignment to occur again. Okay, but that was unweighted. So how would we be able to do that with weighted? Because we were talking about disjoint cores. Well, that's a bit more difficult with the weighted case. In a weighted case, we have that every core gets a weight, and that's the smallest weight of the objective literals in this core. And each objective literal can, in this case, contribute to multiple cores, but the sum of the weights of the cores cannot exceed, for the objective literals, cannot exceed the weight. So let's take a look at an example now, how that works. We again have a temporary objective that's initialized with the actual objective that we are looking at. We have our current partial assignment, and we have an upper bound of 4. So first, using the same idea of how to extract cores, we will find a local core y1 or y2 needs to be true given the current partial assignment. And since the weight of y2 is equal to 2 and the weight of y1 is equal to 7, well, the weight of this local core is equal to 2 because that's the smallest. What we now do is we subtract 2 from the coefficients of the literals in this core. And we continue, we do exactly the same. We find now that given the current partial assignment, y1 or y5 needs to be true, y5 has weight 1, y1 has weight 5, so so it has weight 1. So we update our temporary objective again. We do exactly the same thing. We find a new core with weight 3 now, and we say, hola, 2 plus 1 plus 3, that's greater than 4, greater than or equal to 4. So I have a lower bound now that's greater than or equal to 4. But interestingly, if we have weight 2 and weight 3 together, that's 5. So we can remove the second core and we can continue with these 2 cores. So as long as you get a lower bound greater than or equal to the upper bound, we have found a soft conflict. So that's our conclusion. We again learn a new clause that prevents the same conflict from happening again. So how do you want to certify that? How do you want to prove that? Well, we have found these 2 cores. We can write them easily into the Boolean constraint. And these constraints are derivable by reverse unit propagation. Because we have found them by using unit propagation and found a contradiction when we propagated exactly the negation of these constraints, we know now that they are derivable by reverse unit propagation. Okay, so from these constraints and something else, we want to derive this clause. First, we multiply the Boolean cores with their weights, and we add them up. And then we need something else. We need the model improving constraint. So when you're doing optimization in VeriPB, you always derive the model improving constraint, saying that I have found, if you have found a current best found solution with value 4, so with some value, you can always get the constraint that you want a strictly better solution. And often we want, if we are going to add it up, it's handy to have it in normalized form. So actually, this constraint is the same as this one, except for that I changed this, the smaller than or equal to the greater than or equal, and then of course I need to rewrite this constraint a bit. What I now can do is I can weaken, so I can remove some of these literals by using literal axioms to get exactly this constraint. Why is that handy? We can add them up. And now if you look here, 5y1 plus 5 not y1, that's definitely 5. If y1 is 2, then this will give me a value of 5, but this one will be 0, and the other way around. So if I add up 5 plus 2 plus 3 plus 3, I get 13. Yeah. So I can cancel them on both sides. Now, if I divide by 5, which is the sum of the weights, minus 3, which is the best found objective value so far, minus 1. Oops, sorry. I get exactly this constraint, which is actually the clause that we wanted to derive. And then in practice, MaxCDCL does some conflict analysis on this to shorten the clause, but that's all reverse unit propagatable, just as it is in subsolvers. So that was the basic idea behind proof logging MaxCDCL. But there are some extra techniques in MaxCDCL that are quite interesting. First of all, hardening. So suppose we are in this case, we have performed look ahead. We have found these two cores. We have an upper bound of 5. So we cannot find any other core at this moment. Well, at that moment, we can still see that if we would assign y6 to be true, then we get a lower bound that's greater than or equal to the upper bound. Because we definitely have weight 2, we definitely have weight 1, so that gives 3. But here in the temporary objective, we still have y6 with a coefficient of 3. So if we assign y6 to be true, we get a lower bound of 6, which is greater than or equal to the current upper bound. So what we actually want to derive is a clause that says if x2 is false, if x3 is true, if x4 is false, then y6 needs to be propagated false. That's what this clause means. And in fact, we can also do it with y8, because the same reasoning goes for y8. We have weight of 2 because y1 or y2 needs to be satisfied. We have weight 3 because one of these one needs to be satisfied. If we, on top of that, satisfy y8, we have a lower bound of 6. So again, how can we prove this? We have the same structure. So we have two cores, let's do the Boolean, and we have the model improving constraint. We add them up, and this simplification I did already. So 7 not y1 plus 2y1 plus 1y1, that gives 4 not y1. So that simplification I did here already. And of course, the weight of the sum of the cores cancels out with the current best found solution. Well, the current best found objective value minus 1. So now we can weaken all of the other objective literals So we get now that only y6 is left. So we get this constraint. We just need to divide it by 3 and saturate, and we actually get the clause that's found by MaxCDCL. So that was hardening. Now comes literal unlocking. And we go back to the unweighted case, so the unweighted MaxCDCL. And in the unweighted case, MaxCDCL doesn't really search for disjoint cores. Instead, it searches for disjoint cardinality constraints. So it searches for cardinality constraints for which the left-hand side, so the literals, are disjoint. And such that if you sum them up, the sum of the right-hand side is greater than or equal to the lower bound. So the sum of the right-hand side of these cores is actually the underestimate of the lower bound. Let's look at an example. Suppose that given the current partial assignment, I have y1 plus y2 plus y5 plus y8 greater than or equal to 3. And given the current partial assignment, I have y2 plus y4 plus y6 greater than or equal to 2. So these and these are disjoint, but if we add them up, then we get a lower bound, an underestimate of the lower bound of 5. That's greater than or equal to 4. So we can say, okay, soft conflict has been found. But how to find such funny cores? Well, that's a bit intricate. So we have our current partial assignment. We have our cores over all literals from y1 up until y8. So now next literal that can be assumed false in the search is y9. And we assume y9 to be false. This propagates y1 and y3. I have marked here the 2 literals with blue. And as you can see, y3 is propagated too. So at this moment, I can actually say that, well, but if I want to have an underestimate of the lower bound, I will probably want to assign these 2 to false, because otherwise, yeah, I'm not trying to get it as small as possible anymore. So we now say that y9 unlocks core 1. So by assuming y9, we propagate enough literals to be true in the core to actually already satisfy it. At that moment, we can say for all of the other literals, I can now start assigning them to false. That's the idea. So let's do that. So I assume y5 to be false. This doesn't propagate anything. I assume y6 to be false. This propagates y7. Y7 is propagated through. Oh, but that's interesting, because now core 2 gets unlocked too. Because 2 of the literals are assigned 1. So that means that this core has been satisfied. So I will probably want to assume these 3 to be false as well, since I'm trying to find this underestimate. So let's do that. I remove them. Well, I put them back in the temporary objective. I assume y2 to be false, and I get a contradiction. So at this moment, I can also conclude that given x1 and not x4, so given the current partial assignment, y9 plus y5 plus y6 plus y2, one of them needs to be true. If you look at what happens here, from propagating y9, y5, y2, and y6, I'm forgetting, this propagates to a contradiction, so this needs to be true. So somewhere I have the feeling now, okay, but now I can say that if I have, if I look at all of the literals from y1 until y9, I could say that 4 of them needs to be true. But is that actually true, what I'm saying right now? First try. Let's just add them up and see if we can just do the same thing as we've been doing all the time already. But then, well, we get something in the right way already, but we have these 2's over there. That's a bit annoying because I cannot get rid of these and I want to have cardinality constraints. So how can I solve this? Can I divide? No, clearly not, because then I'm dividing the right hand side as well. So can I actually conclude this? Well, I'll show you that you can. So let's assume y9 to be true to start with. In that case, we know that one of these 3 needs to be true. So that gives us cost 1. 2 of these ones needs to be true. So that gives us cost 3. And y9 itself was also assumed now to be true. So that's easy. If y9 is true, then that's the case. Let's assume now the opposite, that y9 is false. Well, in that case, y9 propagates y3 to be true. So y5, and we can actually replace this score by y3 needs to be greater than or equal to 4. We can just remove y5 and y6 there already. That's the idea. And now the same reasoning goes for y5 and y6. If one of them is true, at least one of them is true, then y3 gives us a cost. Well, one of these, 2 of these ones gives us a cost, so we are at 4, and then the 2 literal from we are at 3. So and then the y5 or y6, the one that is actually true, gives us cost 4. So actually, let's assume y5 and y6 is false. But in that case, we have found that y1 and y7 is true. And from here, we can now find, since y9 is false, y5 is false, and y6 is false, here we have found that y2 needs to be true. So indeed, in this case also, we can replace these scores by this cardinality constraint. So that needs proof logging. And yeah, I can remove the question mark because we now know that it's actually the case. We have formalized this. I'm not gonna get you lost in the complete derivation. I have an extra slide if someone wants to see it later on today or in the questions. But we prove this basically by taking this score and then always adding, inductively adding them up, but taking care when we add them up of these overlapping literals. Okay, so that was MaxCDCL. Kind of. MaxCDCL combines this Benjamin bound solving with solution improving search. Basically by encoding the model improving constraint, saying that I'm searching for a strictly better solution to actually get more unit propagation. And it does so by encoding the this constraint using a circuit based on binary decision diagrams. So how do I need this to read this as a human? Let's say this is the constraint I want to encode, and I will take a look first at x1. If x1 is true, then clearly I still need to look if that constraint is satisfied. If it's satisfied. Yeah. If x2 is 1, then I get to the false state. So if x1 is 1 and x2 is 1, then the constraint is falsified. On the other hand, if x1 is 2 and x2 is 0 and x3 is 0, then my constraint is satisfied. So you just can follow the paths to see if actually is satisfied or not. And this will be translated in a CNF formula in a bit. So, like I said, every node corresponds with part of the original pseudo-Boolean constraint, and every node propagates based on one decision literal, which is always the first one. So they are always ordered somehow. And then if the false node is propagated through, then the constraint in the root is falsified. Okay, so how is this encoded in a CNF formula? Well, for every node, we add some reification constraint and a reification literal. So, for example, V22 is true if and only if 4x2 plus 5x3 smaller than or equal to 6. But interestingly, if we take a look now at these coefficients, well, for the assignments that's smaller than or equal to 6, that's clearly only when x3 is true and x2 is false, or the other way around, or if both are assigned 0, right? But that's also actually the case for smaller than or equal to 7, because you cannot get a combination of the weights of these literals that's equal to 7. So we can actually say that this constraint, smaller than or equal to 5 as the lower bound and 8 as the upper bound. That's the same constraint in some sense. And then after introducing the reification variables, the clauses are added to the solver. So, for example, if you take a look at this one, if V2 is false, V21 is false, and X1 is true, then V11 is also false. Okay. So, how to certify this? Well, first of all, we want to reify this. But how do you reify a constraint that has as right-hand side an interval? Well, it turns out that if we take for the left direction, we take the lower bound, and the right direction, that works. And more importantly, then the clauses are easy to derive. But how can we now prove this? Because, well, simple reification assumes that you have the same right-hand side. So how will we actually get this to work? How will we prove this? Well, we introduce two variables. This one is known by the proof, by the solver. So V22 is known by the solver, and we will first reify them with just the lower bound at the right. And then we'll introduce a V accent. So this one, a V prime, which has as right-hand side the upper bound. And that one is only known in the proof. So that's nothing in the solver, but we just will use this one to actually prove that if this is true, then V22 is also true. And how we will do that? Well, we will just prove somehow that if V prime holds, then just V holds. And then after we've done that, so I'll show you in the next slide, I think, how we can derive this one. But after that, after we have this verification, we can derive the clauses by a simple cutting planes derivation. And it's just the addition of these constraints with the child. But before I will be able to explain how to derive this one, I have to give you some intermezzo. So how can we do in VeriPB a proof by contradiction? Remember from the introduction this morning of the redundance-based strengthening that it is fine to add a constraint C if we can find a witness such that this condition holds. So take an empty witness. the condition that we have there will become F and not C implies F and C. But F is clearly entailed by F and not C. So that can be removed. So the only non-trivial proof goal that we get is, can we derive from F and not C, which is this, not C, and not C, which comes from here to prove that C actually holds in F and not C, can we derive a contradiction from that? And yes, that's what we want, because we want to have proof by contradiction. Is that clear? Because I see some people looking weird at me. Yeah, go ahead.
The green not see under the witness, or is it just two identical not C's?
So this is the C under the empty witness, right?
Okay,
but then to prove that C follows from this one, we can give a cutting planes derivation that from this constraint, the negation of it, it follows that under the witness, it follows that 0 greater than or equal.
I mean, if you phrase it in a slightly different way, suppose you have an empty witness, and suppose you're doing redundance with an empty witness, then you're going to do a proof by contradiction without loss of generality, because again, as Dieter said, F implies F, but now you realize that, okay, but if from F and not C, you're able to derive C, then just syntactically, whenever you take a constraint and its negation and add them up, both sort of it's suggested by the notation and also purely syntactically, they will just vanish and leave 0 greater equal 1. So if you can actually carry out the next to last line, then you can also derive contradiction. So a sort of a redundance-based strengthening step with an empty witness is exactly a proof by contradiction. Sort of the same thing.
Yeah. And then proof by case splitting. So if we have a proof of X implies some constraint and not X implies some constraint, which is actually written there into the Boolean format somehow, well, then we want to derive that this constraint actually holds, right? And following the completeness of cutting planes, this needs to be possible, right? And there is someone who wrote a chapter on proof complexity in the handbook of SAT, and they say, sorry, we don't know how to do this. And there, by the way, it's called fusion resolution. If you ever did that. Luckily, we are able to do that, and that's a proof by contradiction. And I have an extra slide in the backup slides if you want to see that. So again, let's come back at our previous problem. We want to be able to derive that V prime implies V. We'll do that by case splitting. Namely, if X is true, then V prime implies V. If X is false, then V prime implies V. So if we then apply case splitting, then we can clearly conclude that V prime implies V. That's the idea. Okay, so I will show you how to derive this clause. What we already have here is for V22, we have the V and the V prime defined. And for the child, for V3, we have already the right implications derived. So these are the constraints that we need to use. And we do this by contradiction again. So we will prove this one by contradiction. So we will assume the negation. So we can assume that X2 is true, V prime is true, and V is false. And those are the constraints that we have. So from the fact that V prime is true, if we look at the definition over there, we can see that Vx2 plus 5x3 smaller than or equal to 8. That's just by using the definition. But now by using the fact that x2 is true, 5x3 is smaller than or equal to 4. So we just fill x2 in here, and then we get this constraint. But if we now look at the definition, 5x3 smaller than or equal to 4 exactly means that v3 is true. So that's one side. Let's start now from the negation, from not v. Well, from not v, we can derive that so v is true if 4x2 plus 5x3 is smaller than or equal to 5. So the fact that v is false means that this is greater than or equal to 5 plus 1. We can weaken x2 at this moment. So we get 5x3 greater than or equal to 2. And then using the definition of v3, which is in this case, this one.
Right.
So,
If you want it on the right. No, wait.
no, I want to have the opposite direction. If this is false, then this is false.
Yeah, okay.
So v3 is false. But that's contradiction, right? Because I just said that v3 is true. So by combining, by adding these two up, I get the contradiction I want to have. And the same reasoning can be applied to get the opposite direction. So the opposite clause. So when x2 is false in that case. And actually, I have lied a bit. MaxCDCL does not use BDDs, they use MDDs. And the idea is that if you, for example, have the constraint x1 plus x2 smaller than or equal to 1, well, then you can branch on the value of x1 and x2. So if x2 is true, if x2 is 1, then you know that x1 is false. So you can already go to this node and so on. And actually, the proof logging is very similar to what I just showed you, except that you need to do the case splitting that we just did on every single variable and on the else case. So on the case where all of them are false.
Maybe it's slightly, but in this case, actually, there's 3 outgoing arrows out of these 2 top nodes.
Yeah.
Right. So, but there's 2 that accidentally go to the same node. But
Yeah.
it's no longer binary, which is where the n comes in.
Yeah, indeed. So that's why you have multi-valued. But I should maybe draw differently. So, what will be next? Well, first of all, first let me wrap up. We have shown you how to provide proof logging for MaxCDCL, which is a branch and bound solver that includes interesting clause learning, and we have shown how to encode, how to proof log the encoding of MDD encodings. And luckily, proof logging is possible with VeriPB, and we are currently submitting a work in progress paper to Pragmatics of SAT. So what's next? First of all, implementation. So what I have shown you is definitely not ready. We still need to implement it, perform experiments. And after that, it might be interesting to have implicit hitting set solvers, because then we would have a solve for every 4 of the different categories of MaxSAT solvers. And who knows, one day we will have a certified track in the MaxSAT competition. And of course, other fields of combinatorial solvers, which I have seen here that really interesting things are happening already. So that's it. Thank you for your attention.
Questions for Dieter?
Have you found any bugs in solvers yet?
Well, not in this one. In RC2 and CGSS we found a bug.
So is it clear how this performs? Like how does MaxCDCL stack up against the competition? I don't know if this is a question to Dieter or to Jeremias or both, but
We talked about it on Monday. Sorry?
As a pure version, it's the second to worst performing one. But if you combine it with some other algorithms, then it's pretty good.
I'm maybe interested in this in slightly different reasons, but your MDD encoding of a single pseudoboolean constraint, does that generalize to, like, say, if you had to? I know you wouldn't need to for an objective function, but with the is this a novel encoding that's part of this work, or is this an encoding that exists?
No, this is something we did.
Yeah.
So the proof logging, of course.
Yeah.
But how this works for multiple, well, I guess you can reuse if you have the same node. That's what you're asking. If you have the same node with the same variables, the same right-hand side, so the same interval it's looking at, and the same utmost one constraint, I guess you can reuse the definition of that one.
In general, if you're building reduced BDDs, so let's look at the BDD side. What they will do is they will just, if they see that you have the same two children, reuse the node.
Yeah.
So
there's nothing stopping you from building a BDD representation of a collection of PB constraints.
No. That's
Kind of what MaxSAT is.
Yeah. So it's ringing bells in many ways, but anyway.
so two questions. One is if you could go back to this fusion resolution slide, just to point out, yeah, here it is. So this is like an extremely annoying thing. And maybe paging the theoreticians. Like, suppose you have cutting planes, I can give you division, I can give you also saturation. Again, by implication completeness, there is a derivation of, simply by case analysis. Either X is true, well, then the constraint on the right tells you that the summing over the B's is at least capital B, or X is false, and then the guy on the right tells you the same thing. So there is a cutting planes proof of this, right? And I will allow any rule you like. Division and saturation, you can have them both. Is there a proof of this? Like a short proof, with constant number of steps, or could we actually argue that could we get something like a lower bound for this? So interestingly, maybe just I'm sort of making a small detour, but we mentioned previously that saturation is sometimes provably better than division. So suppose that this A actually was the same as the B, and suppose that these subsets of variables were disjoint somehow. Then it's sort of clear. Oh no, I have to touch the. Okay, let me take a step back because I need a slightly more complicated example. But something that is looking very, very close to this can actually be used to formally prove that this kind of one-shot derivations that you can do with saturation to push up your coefficients, and you just can't do it with division. But this example is like slightly different, and you realize that the problem is that somehow, even if you, regardless of whether you try to do saturation or division on this one, you're going to pick up like a lot of annoying coefficients. Like you're going to pick up a coefficient 2 here if you just add them up, for instance. If you add them up, you get cancellation of X. But then you get B minus A on the right. Well, that's me. And then you get 2 times BILI, which is like not what you wanted. And I really don't. It's not like I spent tons of time thinking about this, but it's like it's such a natural rule to just allow you by case analysis to derive this constraint from the other two, and it's kind of annoying that. I just don't know how to do it. Again, I didn't spend tons of time on it, but it seems to be something that I don't know if this is beyond cutting planes or.
I mean, you can do it without. I mean, we cannot. I don't think it's particularly helpful, but like with just extension variables.
Yeah, no,
instead
you
of-
can do it with extension. And again, I mean, redundance without the witness, it's very easy to do it with. And this is another observation. Like, if you don't like the syntactic, you realize it sort of follows from what's said here, that you can throw away all the syntactic rules for cutting planes and just have redundance. Because redundance with an empty witness will allow you to do proofs by contradiction. And that in particular, like any addition or multiplication or division, you can always you could always do these proofs as well. The assumption that the consequence doesn't follow from the premise is like bizarre. But I guess we have these syntactic rules because it's somehow nicer to think about it that way.
And also, we do need the syntactic rules inside the proof by contradiction.
Yeah. Yes. Yeah. Sure. That's true. Another thing I was a little bit curious about in the taxonomy of like MaxSAT and pseudo-Boolean optimizing solvers that we had, was it yesterday? Like, where do this branch and bound fit? Does it fit somewhere? Because it's sort of, I mean, it's collecting cores.
That was one of my open questions.
Oh, that was one, because it is collecting cores and it's doing like local OLL style rewriting. This trick fiddling with the coefficients is kind of the OLL rewriting.
No, it's not adding anything.
No, but you're doing it inside your head. Right?
So the
I
thing
mean,
that-
you're sort of adjusting coefficients in exactly the same way.
Sort of weight-aware core expression.
Yeah.
Yeah, we had a paper on that in 2016.
But the rewriting that OLL doesn't do, but that you should mentally do in order to understand it, is
Yeah,
also what they don't do, but mentally
It's
do
a
to
trivial
understand
case,
it.
so you have an almost disjoint set of cores, and then it's trivial to compute the disjoints already.
No, but even the way you were, no, I mean, when they were incrementally updating the coefficients, it's like, I mean, it is the OLL rewriting, right? Even if you have overlapping cores in the way.
If you don't mean by rewriting the introduction of the actual encodings.
Yeah, you don't need to do anything.
No. But
So it's
the
a thing that you
the
do
way I'm
mentally
massaging the
during-
objective
Yeah.
is sort of the same, and the rest I think somehow I do inside my head, kind of.
It's the same thing we do in PB-OIHS. This extraction and modifying the objective to get cores that overlap.
Yeah, no, you could do it, but it's sort of similar in spirit, but also different. Yeah. Other questions, comments? We thank Dieter again.